Hi, I'm Inez, and this is Paul. We are both members of our MDX team at Blog. MDX team at Blog is mobile developer experience. We mostly are concerned with the reliability of the tools that we provide our developers with. It's the IDE, build systems, CI systems, testing infrastructure, both physical and as well as virtual devices. And today we want to tell you about our CI story. In our CS story, we had a lot of lessons. We overcame a lot of problems. So we want to share our lessons, tell you about some of the wins we had, and some of the remaining problems that we will solve in the future. So let's start maybe with some numbers. Currently at Blog, we have over around 250 Android engineers that our team supports. And those 250 engineers ship 11 Android applications. So we have 11 major applications that they all go to Google Play Store. And on top of that, we have around 250 smaller Android applications. We call them development applications or the demo apps, which are meant for testing part of the code or working just on the subset of the code. It allows developers for faster experience, faster build times, and just more pleasant experience when developing. And when it comes to the complexity of our code, we have around 5,500 modules. And that's the number that is really growing fast for us because just in December last year, we had about 3,700 modules. So that's a roughly 45% increase just in less than a year. And before we talk about the details, let me also tell you about the composition of our CI pipeline and what that pipeline looks like. So in our pipeline, we have a few different main type of jobs. We have checks, which are like typical K-link checks or checking for unused Gradle dependencies and alerting. Then we have builds, so basically building APKs or AABs of our applications and tests. Typical unit tests, UI tests, and publish. Publish in our case publishes to either Play Store or to internal artifact store. And those jobs, those are just the types, but really we have around 1,200 of those jobs for any build. So this here is an example of what our pipeline looks like. Going from left to right, we start with building the applications, building the tests. It all happens in parallel as much as we can. And then when we are done building, we start testing it. And then eventually when we finish testing, we upload to our artifact store. There is also the results collector, which in our case is a no-op job. It's meant to make sure that every test and all the checks pass before we start any publishing. We want to be sure that for every hash, every SHA, we either have all the artifacts or none of them. It just makes the conversation about it much easier. So let me tell you about the problems that we run into with this setup and how we solve them. So first one, when we got to that number of having 1,200 jobs for every CI build, every pull request, first problem was the Git performance. We basically weren't able to clone as much and as fast. So we tried using obviously shallow clones. Then we tried using NFS, but none of those scaled for us. So we went back to the drawing board and came up with the solution that eventually worked for us, which is using Git snapshot and Git bundles. Snapshot in our case it's a archive of our repository that we take every night for every repository, and that's a snapshot of current state for given date with a little bit of history. We don't provide a lot of history. It's a shallow clone of depending on the repository, but up to 50 of that. So that lets developers in the CI run certain Git operations so they can understand, for instance, what are the changes, what jobs they should run for particular changes. And then for every shadow we build in our build system, we also create a Git bundle. And in our case, Git bundle is a differential between the latest snapshot taken that night and the current SHA for particular build. So this is pretty effective because we can store it in S3 and virtually it scales indefinitely for us. On top of that, we have workers in EC2. So when we download data or upload to S3, it's very cost effective. So that was the solution that let us scale indefinitely, essentially, for our scale. And we are using it now across all our repos, not just the biggest ones. So the second problem, now at this point, we solved already that we can run a lot of jobs, and the number of jobs and number of applications kept growing. So the second problem that we ran into was around UI tests. We rely heavily on UI testing. We have a lot of jobs responsible for performing UI tests. There are some numbers. We have around 14,000 unique UI tests, and they run across 500 CI jobs. And they're not all equal. Like, for instance, some jobs run over 3,000 tests in one CI job, and the other ones are much smaller, just run 5 or 6 or 7 tests. That became very, very expensive for us to run hundreds of those jobs every day. So again, we looked into what we could improve here. And we find a solution that we call UI test avoidance. And it's relatively naive and simple solution that looks at the APKs that we are about to test. So in our pipeline, those are the inputs to the UI tests app shards. So there's an application APK and the test APK. And we take a hash of those. So when we find out that we already tested certain combination, we skip testing it altogether. We just reuse the old result from the prior run. And again, this is a simplified example. Really, we have on the real chart for our pipeline, there would be about 1,200 of those shards. So that's a solution that is naive and worked really well. However, we had to accommodate for some of the things. This is just a pseudocode showing that, for instance, when we build APK, the process is not fully deterministic. So we had to accommodate for the fact that different files ends up in different text files. We also have the inject build ID. So we had to accommodate for that fact and basically normalize. And one important fact about hashing APK is not that we actually hash at the end of the day the APK as a single artifact, but we decompile it. So we use the APK tool to decompile our APK, and then we can do a bunch of transformations, normalizations, and then it's ready for hashing, and that way we get a consistent hash between different non-deterministic builds. So once again, like relatively straightforward solution, but gave us really good results. For our biggest shards, which I mentioned before, like the point of sale in our case, we got saving around 25%. So we run tests much less than before. And for hundreds of the smaller apps, we have savings of around 98%. So we barely run them now. And that was our solution for this problem. And I will let Paul talk about our other problems.
Thanks, Inez. So awesome. So up till now, we've talked about some of the numbers, the problems that we faced, and with scaling our applications and the monorepo and avoiding unnecessary UI tests that we run. Something important that Inez mentioned was we often found ourselves in a situation where the UI jobs that we're running, we're basing this UI test avoidance strategy off the fact that the two APKs that were provided as input were essentially the same. So we thought of a way to bubble that up one level higher in our CI pipeline to see if we could actually avoid running a job altogether based on some of the hypotheses that we had. That is, if we run multiple builds that produce the same or similar artifacts, then the changes introduced in those builds were not significant enough to require running particular jobs. And that's where we came up with this name, shard avoidance. And shard here kind of refers to the name of a job. We use them interchangeably, but essentially that's the inception of this project. And a couple of reasons outside of the obvious, which is reduction in build time as a benefit of shard avoidance. We oftentimes have shards or jobs that have flakes in them. So changes made by developers that don't contribute to a test failing or intermittently not passing can cause flakiness in these jobs. And so potentially by not running those jobs, we reduce the number of potential flaky tests that would be run. We also reduce the worker queue. So the less number of jobs that have to run in the CI pipeline, the less queue there is. And eventually this leads to developers being able to iterate on their changes faster. So how does this work in practice? Essentially, it's a 4-step process in determining shard avoidance. In the first step, we have something called an analyzer, which consumes this list of modified files in a particular change, and we compare the SHAs from the Git history that we have in our CI pipeline. The analyzer takes those files and it then maps them to Gradle modules. So Gradle is our build tool. We do an internal mapping of those changes. And then once we know which Gradle modules were affected, we're able to map it to those shards or jobs, and the CI is then able to run with a minimum number of jobs possible. So let's take a look at an example of the previous CI pipeline that we just discussed. In this example, all these jobs run each time we run a build. We have defined Pathfinder as our entry point, which is just the name of the entry point shard or job that does the analysis to run which minimum set of CI jobs to run. And the dependent shards are then run in parallel whenever possible and eventually collected into a results collector. So up until UI test avoidance, we could see that within each shard that runs UI tests, we could avoid certain tests based on the changes if the APK in the APK that had no impact to those test functions. But what with shard avoidance, what actually happens is something like this. For our non-convergence CI pipeline, this is a simple illustration like Inez mentioned before. We actually have 1,200 shards, but in a simplified world, in our CI pipeline, Pathfinder would run. The responsibility of Pathfinder would be to find the minimum set of CI jobs to run. Inside the job, it would then consume a list of files that have been changed or modified. And this part of the analysis is fairly cheap. Finding a diff of Git files that were modified for us benchmarked at about 200 milliseconds. So it was a fairly cheap thing to analyze. But in addition to the changes of these files that we analyze, we also need a model representation of a build graph to see if any dependencies had changed. So our mono repo, as mentioned before, contains over 5,400 such Android modules, and creating a dependency graph for this size of a project doesn't come cheap. It's something that we've iterated over the years to make more efficient. In the example here, we see that a non-convergence branch, what would happen is if a developer made some changes that didn't affect, like in this case, app shard 1 or app shard 2, it would skip running those shards altogether. And in addition, it would skip running any shard that was also dependent on that. And so there's a little bit of a cost here that I mentioned, which is creating that build graph. And we visited other solutions, like tried using Bazel, and there was a set of developers that were invested in that in the past, but that does come with a steep learning curve and a massive effort to migrate the entire mono repo over. So we continue to use Gradle as our source of truth here. And Gradle offers a way to receive these project models and graph data the same way IntelliJ or Android Studio communicate with Gradle. We use the tooling API the same way, which provides us the capability to receive and inject the build graph. The data model representation is mapped to our Gradle modules, which map to the shards based on the parameters that we define. But it is important to mention that this transaction isn't cheap. There are various phases that Gradle goes through, and namely like the configuration phase where we evaluate the build and parse the build scripts and create the project models. Comes with a cost for our analysis. The underlying avoidance analysis results that we got were that over a span of about a year, we noticed that 50% of the shards, which is about 600 shards, were skipped on average, and 360 hours estimated of time savings. The problem is still there in the sense that there's one more area of obvious improvement, which we knew that we could bypass by if we were able to kind of improve the Gradle configuration phase, which took up about 12% of our total build time. So we started thinking of different ways to bypass that. And one of the things that we thought about was using a static build analyzer. Since we use Groovy build files, we were able to initially come up with a proof of concept that created this dependency tree just statically analyzing our build files, and it reduced this 3 to 5 minute overhead that came with running Gradle's configuration phase to merely about under a minute. But it came at the cost that we later realized that our build logic in our app had very opinionated concepts that we weren't able to automate. And so that came at the cost of a level of correctness for what our dependency graph actually looked like. So we took a step back and went back to using Gradle. And eventually we came up with a solution, which we call a shard avoidance cache, which is, first we needed to answer how, if we needed to invoke Gradle as much as we did, how often were developers modifying files that would cause changes to the actual build graph? Was there ways to solve the build graph so that it could be reused by other developers? And what were the trade-offs? So we did an analysis where we looked at these files that we call global files, which are essentially, settings.gradle or build.gradle files, and see how often were they actually modified. And we came to see that only about 8% of the time developers were touching these files, which would trigger our build graph to be recreated. So using this information, we essentially took the output from Gradle's tooling API and cached it in S3 key value store, keyed against essentially what was those global files, the contents of those files, as well as the path, a hash of both of those put together, and we're able to reuse those across all the pull requests that our developers make. And so just from that phase alone, we were able to see that an overall 12% reduction in our overall build time, 90% cache hit rate on those shared cache hit rate on our avoidance cache, as well as a 63% time savings on the avoidance analysis, which is the entry point shard that we talked about earlier in our CI pipeline. And this is kind of a snapshot representation of the time from when we started the project of avoidance cache to when it was actually released. So you can see at the peak, it was taking anywhere between 11 and a half, 12 minutes to run this analysis phase. And as soon as we had released it in about early to mid-May, we saw that decrease to about 4 to 4.5 minutes. So it's been a journey for us working on the Android CI pipeline on Square. And just to recap some of the problem space and solution, we started off by discussing the type of scale that we deal with in our CI ecosystem. The system comprises of handling 11 applications that are built within one mono repo. The repository is shared across over 200 developers that are actively contributing to it. And we have over 1,200 shards or jobs that run per build that contain over 14,000 UI tests. So the time cost associated with this is heavy, and the jobs themselves can be dependent on each other for various reasons. And so the solutions here that we saw, first that Inez talked about, was the UI test avoidance, once we were able to figure out that those APKs that were ingested into the shard that allowed us to do that, we funneled up one level higher to be able to avoid shards altogether that don't need to run, and eventually cache the output from Gradle so that we could reuse that build graph to create the cache for other developers to reuse. So those were our key problems. Those were our key wins. And with that, Inez and I would like to thank you for listening to our talk.
Yeah, thank you.